Hello and welcome. This video covers the results of reliability and failover testing that we completed using the Apache ActiveMQ environment. We used version 5.11, which was the generally available release at the time of testing. Now, this diagram provides a view of the architecture that was implemented for our testing. Using this architecture, the goal was to cover service availability through clustering, which in ActiveMQ it's referred to as a network of brokers. And we also wanted to provide message reliability using the ActiveMQ master-slave failover. And as you can see, each master broker has a corresponding slave broker on another server. Here we have a summary of our test results, and you can see that we completed a number of tests, including simple network interruption, regular shutdowns, and server failure. We checked for message duplication and message loss in each case using both point-to-point and publish and subscribe models. In general, when an ActiveMQ broker was stopped either manually or via a power failure, the failover worked as expected with zero loss or message duplication. However, in all cases of a temporary network outage, we discovered issues of both message loss and duplication. On further investigation, all these test failures came down to what was referred to as a split brain issue, and we'd like to go ahead and demonstrate what exactly is happening in this scenario. Now, rather than demonstrate this using our entire environment, what we've done is we've taken it down to just 2 servers, since this is all that's actually required to duplicate the problem. First, we'll start up both master brokers, one on each server. And once they're up, we can go ahead and start up the corresponding slave brokers. And just to verify, they were unable to obtain the lock, which means they're in slave mode. So let's go ahead and open up the console for broker number 1. And the admin console for broker number 2. Now, I should point out that for this demonstration, we are simply using point-to-point fire and forget messaging to allow us to show what is happening in the different queues. So we'll go ahead and create a queue for testing purposes. And we'll go ahead and send 15 messages to the queue. And now we can see there are 15 messages in the queue. Now we'll go ahead and disconnect the network cable to trigger the failover. And this typically takes about 1.5 minutes, so what we'll do for sake of time is just pause the video and we'll be right back. So now we can see that the slave broker for broker 1 has been able to obtain a lock on the persistent store and is being elevated to the master position. If we go ahead and open the administrative console for the new elevated master, as expected, we can see that it has indeed recovered the 15 messages that were originally in the queue. And also as expected, the administrative console for the original master no longer gets any response from the server. Now, to show where the problem actually arises, we're going to go ahead and send 25 messages to the new elevated master. And if we go back and check the queue with a refresh, we will see the expected 40 messages. Now let's go ahead and restore the network connection to server number 1. As expected, the elevated master still has 40 messages in the queue, but what we see is that the original master comes back as a master instead of a slave, and it still has the first 15 messages that were recovered by the elevated master, meaning that these are now 15 duplicate messages. Essentially, this scenario results in two masters operating with their own queues and functionality, which not only introduces those duplicate messages, but also means that both the original master and the elevated master are functioning without corresponding slaves, and as such have no failover protection. So if either one of these masters were shut down, there is a risk of lost messages. As mentioned, this particular split brain issue had cascading effects for the rest of the related testing. Now, this scenario was completed with the default KahaDB persistent store on an NFS file share, and in an attempt to eliminate the issue, we also investigated using JDBC as the persistent store. However, in the case of JDBC, while the original master did not come back as a separate master, it also would not come back as a slave either. In short, the disconnected master process appeared to hang with the service port and the admin console port still open, meaning that the client would attempt to connect and wait for the timeout before moving on to one of the other brokers in the network of brokers. Now, according to a JIRA ticket, the actual issue may not be with the broker itself shutting down, but rather with Java processes not shutting down because of other items like the Jetty engine that is used for the web-based administrative console. And that concludes the overview of our ActiveMQ reliability and failover testing. And we would like to thank you for watching.